In this lesson, we're going to discuss exponential functions and their applications. In the linear functions you have studied so far, the rate of change has been constant, whether positive or negative. Here's a sample graph of a linear function. Here's an example. f of x is equal to 3x plus 2. Our rate of change for each unit of x was 3. Exponential functions have a rate of change that is not constant, but grows at exponential rates. In other words, between each x unit, the rate of change increases or decreases. And so our exponential functions follow this curved line. Exponential functions are written in the form of f of x is equal to b to the x power. So here's an example graph of y equals 4 to the x. The one thing you will realize is that in the graph, it gets very, very close to y being equal to 0, but it actually never ever equals y equals 0, because if we take a look at 4 to the x, there is no exponent that I can take 4 to in order to get 0. Here's a table of points for y equals 4 to the x. When I plug in negative 1 for x, I get 1/4. When I plug in 0 for x, we actually get the whole number 1. When I plug in the whole number 1 for x, I get 4 for y. And so you can see here on the graph that I have going through 0, 1, it's going up through 1, 4, and it continues to get sharper and sharper as it goes up. So the first thing I'm going to have you do is have you try graphing these two exponential functions. So you can come up with a table of points, and then again try to connect them so they make that sharper curve. So give this a shot. Pause the video. When you're done, restart the video and go along with me and we'll see how you did. Let's take a look at y equals 2 to the x. So I'm going to make a little t-table here. My left column will be my x value, my right, my y value. So I'm going to start similar to what I did before. I'm going to start with negative 1, and 2 to the negative 1 is 1/2. I'll go to 0. 2 to the 0 is 1. Now let's take the whole number 1 for x. 2 to the 1 power is 2. Let's go ahead and do another one. Let's take x is 2. Well, 2 squared is 4. So let's see how the graph would look. So let's go ahead and plot the points and see how our graph turns out. So it looks like at negative 1, we're over here at about 1/2. And then we're going to cross through 0, 1. And then we're going to go to 1, 2. And then 2, 4. So there's 2, we'll go up to 4. So we can get a basic idea of what our graph is going to be like. Now we'll do the other side. I'm going to again do another set of points, x and y. So for this one, I'm going to start with the same numbers. Let's do negative 1. So negative 3 to the negative 1 power is 1 over negative 3, so negative 1/3. Let's take x is 0 again. We're getting negative 3 to the 0 power, still going to come out. 3 to the 0 is going to be 1, but the negative in front of the 3 is going to make that negative 1. Because again, I don't have the parentheses around the negative 3 to say that I want negative 3 raised to the 0 power. So I'll go ahead and run through. Let's take x is 1 again. Let's take x is 2. Negative 3 to the 1 power, so that's negative 3. 3 squared is 9, so negative 9. So we kind of see the general direction we're heading here. So when x is negative 1, I'm actually below the x-axis here. 0, negative 1. 1, negative 3. so it's going down, and 2 is going way off my graph. So it's never going to quite reach the x-axis, but it is going to curve down. Let's take a look at an application. Here's an application using exponential growth. Suppose it takes 12 hours for a certain strain of bacteria to reproduce by dividing in half. If 75 bacteria are present to begin with, the total number present after x days is found with the function f of x is equal to 75 times 4 to the x. So what I'm going to do on this is I'm simply going to, since x stands for days, I'm actually going to go through and plug in the numbers 1, 2, and 3 in place of x and simply do the calculations. Let us start with x equals 1. 75 times 4 to the first power. So 75 times 4, that's going to get me 300. So that's the number of bacteria that is there after 1 day. The second one, after 2 days. So we replace the x with 2, and we have 75 times 4 squared. So 75 times 16, that's going to give us 1,200 bacteria. And the last one, we plug in 3, 75 times 4 cubed, which is 75 times 64, and we end up with 4,800 bacteria. Now I'm going to have you try an application. A painting is purchased as an investment for $200. If its value increases continuously so that it doubles every 3 years, then its value is given by the function v of t equals 200 times 2 to the t over 3 power, where t is the number of years since the painting was purchased, and v of t is its value in dollars after time t. Find v of 15 and v of 21. So pause the video, try out these problems. When you are done, go ahead and restart the video and work along with me to see how you did. So in this particular example, they're giving us what t value is, and we just need to substitute it in. So let's go ahead, and v of 15 means that I'm going to put 15 in place of t. So that gives me 15 over 3 as the exponent. So let's go ahead and simplify. So 200 times 2 to the 5th power, and that's 200 times 32, which is going to give me 9,568. Now let's do v to the 21. Again, substitution. We'll write down the formula 200 times 2. We replace the t with 21, so 21 over 3. Continue to simplify. 21 over 3 is 7, so this becomes 200 times 128, which gives us 25,600. And so this is the value in dollars. We want to mark that with our units there of dollars. Good job.